Welcome back, Sarah. Chapter 2 dives deeper into supervised learning.
Yeah, Jane, it's exciting. We're moving beyond the basics now.
So, classification and regression. Can you give a quick, simple example for each?
Sure. Classification is like sorting emails. Spam or not spam. Regression. Predicting, house prices.
I get it. Different outputs. But what about overfitting? Too complex?
Exactly. Think of it like finding the perfect, ridiculously specific rule for getting a customer to buy a boat.
Too specific.
It works for your current data, but won't work for new customers.
So, how do you avoid it?
More data or less complex models. Simpler rules.
This reminds me of my attempts to train my dog.
It's all about that balance. Lots of data, the right model.
How much data is enough?
More data usually is better.
But what if you have tons of data, but, a lot of it's the same?
Doesn't help. Variety is key.
Great point. So, how does this relate to real-world problems?
Imagine a bank predicting loan defaults. Very important.
Interesting. How does dataset size impact model complexity?
Larger datasets allow more complex models without overfitting.
So, more data is like getting more information, better understanding.
That's the gist. There's a fine line.
So, next, what types of algorithms are used?
Lots of algorithms like decision trees support vector machines.
Super cool. Learning about these is great.
It's all about finding the best fit for the job.
Definitely a lot to learn. Thanks, Sarah.
Anytime, Jane.
Sarah, now we're diving into some actual algorithms. Let's start with KNN.
Okay, Jane. First, we're using datasets, some made up, some real.
Why both?
Synthetic helps isolate ideas. Real ones show the real-world messiness.
Got it. So, what's the KNN deal?
Finds the K closest data points to a new one, then predicts based on their class.
Like one nearest neighbor?
Exactly. Just the one closest point. Prediction. Same class.
Okay, I get the idea, but what about K?
More than one. We count neighbors, pick the most common class.
So more neighbors mean more votes.
Right, and we use a vote.
Neat. This is like classifying a customer.
Exactly, determining if someone will buy a boat.
How do you actually use this in code, Sarah?
We split data, use scikit-learn. Fit a model, make predictions.
This is amazing. And how do we evaluate?
Check accuracy on unseen data.
So, these datasets, what's their role in this whole thing?
They help visualize and understand.
That's fascinating. Real-world datasets with tons of features.
Can be tricky, KNN might not be perfect, but it's a great start.
Can you give a brief example?
The Forge dataset. We've got 2 features, 2 classes.
How many points?
About 26.
So, KNN, what are its limitations?
Sensitive to distance metrics, can struggle with high dimensions.
Okay, more on that later. But this is great, Sarah.
Thanks, Jane. Great questions.
What about feature engineering?
We're looking at interactions between features, a deeper look.
Sounds complex, but we'll get there. Thanks for walking me through this, Sarah.
Anytime, Jane. Really enjoying this discussion.
So, Sarah, those decision boundaries, they're showing us how KNN works, right?
Yeah, Jane. More neighbors, smoother lines. Simpler models.
So, what about the breast cancer data? What do we see?
Training accuracy shoots up high with few neighbors, but test accuracy plateaus.
Overfitting. Can you explain that trade-off?
Too much focus on training data misses the general trend.
So, there's this sweet spot for K?
Looks like around 6 neighbors is good for this data.
So, choosing K is key?
Yes, but depends on the dataset.
What about regression? How does KNN work there?
Averages target values of neighbors.
So, you're basically predicting the average target?
Correct. More neighbors, smoother curves.
This R-squared thing. What's that all about?
How well our predictions match the actual values, 0 to 1. Perfect is 1.
So, an R-squared of 0.83? Pretty good?
Yeah, it's quite good for KNN regression.
And are there other evaluation metrics for regression?
Yes, Amarmisi. Each has different strengths.
So, Sarah, are there any limitations to this KNN method?
It's slow with big datasets, high dimensions. Scaling is key.
And distance measures, are they crucial?
Absolutely. Euclidean isn't always best. Others are possible.
Thanks for breaking it down, Sarah.
My pleasure, Jane. Glad to help.
Sarah, we've seen how KNN can get messy with lots of features. Linear models, are they a different approach?
Yeah, Jane. Linear models assume a linear relationship between features and the target.
So, it's like drawing a line or plane to predict the outcome.
Exactly. Straightforward, but less adaptable to complex relationships.
So, what about the simple example linear regression? Is it always a good choice?
Not necessarily. It can overfit with many features, making predictions on unseen data less reliable.
So, what's this ridge regression magic?
Ridge regression adds a penalty to the coefficients, keeps them smaller, less complex.
So, how does alpha come into play?
Higher alpha, more restriction. Smaller coefficients, possibly better generalization.
Wait, if the coefficients are smaller, isn't the prediction less powerful?
Yes, potentially. But the sacrifice in training accuracy might lead to better test results.
Okay, let's say the dataset has 100 features. How does ridge help?
Prevents overfitting. Keeps the model from being too sensitive to individual features.
Interesting. Any real-world examples where ridge would be better than KNN?
Analyzing stock prices with many factors at play. Linear models help isolate key trends, often more easily.
Okay, so, ridge helps avoid overfitting on the training data?
It does, using regularization to control model complexity.
How much control does the user have in terms of alpha?
User chooses. Higher alpha is more restricted, simpler, potentially better generalization. Lower alpha, less restricted, potentially higher training error, possibly better prediction on test.
So, we're trading off training versus generalizing performance?
Yes, it's a careful balance.
Is there ever a case where OLS, standard linear regression, might be the best choice?
Yes, if the relationship between features and target is truly linear and we don't have a lot of features.
This is a great starting point. Thanks for helping us understand.
Happy to help, Jane. Learning together.
Sarah, those learning curves, they're fascinating. What do they tell us about ridge and linear regression?
Well, you see how ridge performs better in smaller datasets. It seems less sensitive to the training data.
So, lasso, is it just another way to do the same thing?
Lasso uses L1 regularization, forcing coefficients to zero, essentially selecting features.
So, feature selection, is that practical?
Absolutely. Imagine a dataset with 100 features but only 5 matter. Lasso helps us find those crucial ones.
So, is lasso always the better choice?
Not necessarily. Ridge generally gives more stable performance. Lasso can be a bit finicky.
What about linear models for classification? Logistic regression and linear SVC, why are they important?
Those models draw lines or planes in higher dimensions to separate classes.
You know, for me, this reminds me of spam filters. Can linear models help separate spam from real mail?
Absolutely. If you can establish features for each, you could use a model like logistic regression to separate.
Right, so what parameter is key for controlling that? What's the effect of C?
C in logistic regression controls regularization strength. Bigger C, less regularization.
So, you're trading off the simplicity of the model versus its accuracy.
Exactly. Just like alpha and ridge and lasso.
Okay, I'm starting to get it. This is a powerful idea.
It really is for analyzing relationships in data.
Let's say I've got a medical diagnosis dataset. Which model might work better? In what scenarios?
That depends on the features and how many data points we have. Maybe lasso if there's a lot of features.
Okay, thanks, Sarah. This has been super helpful.
You're very welcome, Jane. We're learning together.
We certainly are.
Learning, and it feels great.
Sarah, you know how we talked about regularization and regression?
Yeah, it's all about finding the balance between fitting the training data and generalizing well.
So, how does that translate to classification with models like logistic regression?
The C parameter is key. High C means less regularization, trying to fit the training data closely.
So, more complex?
Potentially, but that can lead to overfitting. Low C, more regularization, simpler model.
So, lower C, more likely to underfit?
Yeah, it's like a seesaw, you know?
So, how do we decide on a good C value?
Well, there's no magic formula. Often, you try different values to see which works best on the test set.
So, test set performance is crucial.
Exactly. It's a balancing act.
What happens with multi-class classification? One versus rest?
We build a separate model for each class to separate it from all the other ones.
Okay, so you're essentially doing separate binary problems?
Right, it's different for each category.
In medical diagnosis, is this method helpful?
Potentially, depending on the complexity of the relationship between symptoms and outcomes.
What are the limitations, though?
Linear models assume a linear relationship between features and classes.
So, if it's not linear, a different approach might work better?
Yes, that's often the case.
Right. It's tricky to interpret coefficients in a multi-class setup.
They get a bit convoluted, you know? It's harder to say exactly how each feature contributes.
Interesting. It's a trade-off.
Absolutely.
It's like choosing the right tool for the job.
Yes.
I see. The impact of C and regularization in classification, it's all about balance, huh?
Exactly. You gotta make sure the model doesn't overfit or underfit.
I think I'm starting to get it.
Great. We're learning together.
Sarah, we've seen how those binary classifiers combine to make multi-class decisions. Fascinating.
Yeah, it's like a team of experts, each tackling a different opponent.
So, when would you choose a naive Bayes model over a linear model?
Well, naive Bayes is lightning fast. Think massive datasets, spam filtering, for instance.
So, speed is a huge advantage?
Absolutely. Naive Bayes works well with high-dimensional, sparse data.
And what about interpretability?
Well, naive Bayes is often simpler to interpret. You can easily see which features play a role.
But is there a trade-off? Linear models might be more accurate in some cases.
You're right, Jane. Sometimes linear models give you better performance, especially with data where features have a more complex, maybe nonlinear relationship to the target variable.
So, it's a balance between speed, simplicity, and accuracy.
Exactly. It's choosing the right tool for the job.
So, the C parameter is crucial, but how do we actually find the best value?
You're right, it's a delicate balancing act. In practice, we usually try different values, typically using logarithmic scales, to find the one that works best for the dataset.
You've mentioned correlated features making coefficient interpretation harder. What happens in multi-class situations?
Well, multi-class makes it even trickier because the coefficients aren't directly showing the relationship between a feature and one specific class.
So, it's about trade-offs again. Accuracy versus interpretability?
Precisely. For instance, if interpretability is critical, maybe naive Bayes or simpler linear models are worth considering, even if they aren't as accurate.
Okay, I see.
And remember, decision trees are a good alternative for more complex nonlinear scenarios. Their if/else nature makes them intuitive to interpret.
I see.
Method chaining is a useful feature in scikit-learn, but it's not always optimal for readability. Sometimes, splitting the fitting and prediction can make the code cleaner and more maintainable.
Right, clear code is also important.
Exactly. Depends on the situation. And always remember to validate your results with unseen data.
This has all been so insightful.
It's fascinating to see how these tools, with their strengths and weaknesses, fit different needs.
We really are learning a lot about machine learning today. Sarah, we've looked at linear models. Now, decision trees. Completely different beasts.
Yeah, totally different approach.
So, when is a tree a better choice?
When you have complex relationships, nonlinear data.
So, like with medical images, maybe?
Exactly. Decision boundaries are not always straight lines.
That visual of a complex boundary in the tree, that's fascinating.
It's about breaking down data into these regions.
How does a tree deal with overfitting?
Pre-pruning, like limiting depth or the number of leaves.
So, a shallower tree avoids memorizing details?
Precisely. A simpler tree will generalize better to unseen data.
But how do you measure feature importance?
The tree itself is splitting based on what it finds most helpful.
And how does it relate to feature coefficients from linear models?
Completely different interpretation. Trees look at features used for the split, not direct correlations.
But what about non-monotonic relationships? A feature that's not always increasing or decreasing with the class.
Trees can handle those cases easily. That's one of their strengths.
So, trees are intuitive, but are there downsides?
They can be overly complex, especially with a lot of data.
Overfitting is definitely a concern.
Definitely. You have to find the balance.
So, a shallower tree might be simpler, but less accurate?
It's a trade-off. Balancing accuracy against simplicity.
I see. How does one choose which method to use, then?
It depends entirely on the dataset and the problem you are trying to solve.
Right, a lot of variables. Fascinating stuff, Sarah.
Really is. Decision trees can even handle regression.
That's a new twist. I see the need for a balanced approach to building models.
Absolutely. You need to be aware of the data's nuances and pick the right tool.
Thanks, Sarah. Really helpful.
My pleasure, Jane. This is a fascinating exploration.
Sarah, so single decision trees, we saw, can overfit. How do ensembles help?
Well, they average out those overfitting tendencies.
Like, how does a random forest do that?
It builds many trees, each trained slightly differently.
Slightly differently? How's that achieved?
Randomly selecting data points and features for each tree.
So, each tree sees a different view of the data?
Exactly. Bootstrapping and random feature selection.
Interesting. So, what's the role of max_features?
It controls how many features are considered in each split.
More features, more similar trees, I guess?
Yes, they are more likely to overfit together.
And fewer features?
More diverse trees, reducing overfitting.
So, how many trees do we need?
It depends. More trees is better, but there's a trade-off.
Yeah, computational cost. A random forest is actually more complex to build?
It is, but usually much more accurate than just a single tree.
So, linear models versus random forests. Which is better for nonlinear relationships?
Random forests are often a much better choice.
So, this is one powerful advantage?
Definitely. It helps to avoid relying on a single tree.
I get it. What other ensemble methods exist, if you know?
Gradient boosting, for example, is a popular alternative.
Interesting. So, a lot of factors to consider.
Precisely. You need to understand the data's subtleties and choose the right tool.
Thanks, Sarah. Very insightful.
My pleasure, Jane.
Sarah, so random forests, we've seen how they average out predictions. How does this translate to a better model?
They smooth out the errors, from individual trees.
Interesting. What's the difference in visualizing individual tree splits versus the forest's decision boundary?
The forest decision boundary is much smoother.
Like more refined?
Yes, because it combines multiple views.
So, if max_features is low, trees are more different?
Exactly. More diverse.
And more complex, right?
Potentially deeper, yes.
So, gradient boosting, different approach?
It's serial learning. Each tree corrects errors of the prior.
How's the learning rate involved?
It controls correction strength,
So, less randomness in boosting?
Less random feature selection, but it is usually pre-pruned.
When would boosting be preferable to a forest?
For high accuracy on a particular dataset, forests tend to be more general.
So, it depends on the problem, you know?
Precisely. Which model is better is highly dependent on the dataset.
And max_features, a crucial parameter?
Yes, usually tuned to a default square root of features in classification.
Do more trees always mean a better result?
Not necessarily. Computational cost increases,
So, best practice is building as many as you can afford?
A good rule of thumb, yes. You want to balance accuracy and feasibility.
So, what happens with sparse data or very high-dimension data?
Forests are less ideal in such cases. Linear models might be better.
Thanks, Sarah. Great insight.
My pleasure, Jane.
Sarah, you mentioned gradient boosting is serial. What exactly does that mean?
Each tree learns from the mistakes of the previous one. It's like iterative refinement.
So, more complex models might mean more overfitting?
Potentially. The learning rate controls how much each tree adjusts. A lower rate might need more trees to achieve similar complexity.
Interesting. So, XGBoost, is that just a faster implementation?
Exactly. It often performs better, especially for big datasets, even though it's more finicky to tune.
How does it actually help with very large datasets?
It has clever optimizations that make it faster to train.
Okay, now let's talk SVMs. What's the kernel trick?
Instead of adding new features, it computes distances in higher dimensional spaces, making models more flexible.
What does it mean to measure distances in higher dimensions?
The kernel function does the work of mapping.
So it avoids the computational cost of creating features.
Precisely.
So are the support vectors just the most important data points?
Yes, they define the decision boundary, just those that lie on the border.
And the Gaussian kernel? How does it work?
It's like a bell curve measures similarity. The gamma parameter controls the curve's width.
A narrower curve?
Means points need to be closer to be considered similar.
How does adjusting C change things?
That's a regularization parameter. It affects the complexity of the boundary. Higher C means a more complex boundary potentially overfitting to the training data.
So, when would an SVM be better than a random forest?
When nonlinear separation is crucial, SVMs excel at complex boundaries.
So, it depends on the shape of the data?
Absolutely.
Thanks, Sarah. That makes a lot of sense.
My pleasure, Jane.
Sarah, we've been looking at SVMs. Now you're showing us how sensitive they are to data.
Yeah, they need careful data prep. It's not like random forests.
So, what's the secret sauce for scaling?
You need features to be on a similar scale. Think of it like balancing a seesaw.
So, if some features are way bigger, they dominate, right?
Exactly. The RBF kernel calculates distances. Huge differences skew the results.
So, we saw how to scale it manually. How important is that?
Critical. Look at that overfitting we saw with unscaled data. Massive difference when we fix it.
Okay, but what if scaling doesn't fix it? Are there other kernels?
Absolutely. There are polynomial kernels, sigmoid kernels, lots of different ways to measure distance.
So, C and gamma, those are important SVM settings?
Totally. C controls the influence of each data point. A larger C allows more influence, but too much and you overfit.
And gamma?
Gamma defines how close points are considered in the RBF kernel. Small gamma means lots of points are close.
So, a smaller gamma gives smoother curves, right?
Yep. Less complex boundary.
How do C and gamma interact?
They often need to be adjusted together. It's like finding the best balance on the seesaw.
Now, neural networks. What's the difference?
Neural nets use layers like adding more processing steps.
Like what?
Weighted sums, nonlinear functions, much more complex.
So they could capture incredibly complex relationships.
Exactly. But tuning them can be a real challenge.
Thanks, Sarah. This is fascinating.
My pleasure. Learning these differences is key to building effective models.
Sarah, neural nets, so much more complex than SVMs.
Yeah, it's a whole different beast.
But, the tuning seems overwhelming.
Well, hidden layers activation functions.
How do we choose hidden layers?
More layers means more complex functions. It's like giving your model more tools.
More hidden nodes, right? Does that always mean better accuracy?
Not necessarily. Sometimes it overfits. You need the right balance.
Okay, so how's the activation function important?
ReLU and TAN, they're like the brains behind the model, how the data is processed making those decisions.
So, TAN is like a more complex curve than ReLU?
Kind of. Think about how they squash numbers.
Right. So, alpha, regularization. What's that magic?
It's like a fine-tuning knob. Stops the network from getting too focused on details.
So, more alpha, more regularization? How do you know the right amount?
It's an art. You experiment.
If we scale data, does that help a neural network?
Huge difference. Data needs to be on similar scales.
Why?
So no feature dominates. Like trying to balance a seesaw.
So more iterations might improve training but not generalization?
Often that's correct. Balancing complexity and training time is key.
But, what about the convergence warning?
Sometimes the algorithm can't find the best solution within the allowed steps. You have to increase the max_der.
So, what's the black box nature of neural networks?
You can see weights connecting layers, but interpreting them can be tough.
Okay, so, how do we find the sweet spot?
Trial and error. Experimenting with parameters.
It's like hunting for the perfect balance.
Exactly. You try different settings until you find what works best.
Interesting. I can see how this can take a while.
It's often about finding that delicate balance.
How does scaling data affect the performance?
Scaling is crucial, just like in SVM models. Otherwise, some features can overwhelm others in the learning process.
Fascinating. This sounds like a detective game, looking for the clues to get the right results.
Exactly. It's about careful experimentation. Often with neural networks, a good starting point is the default parameters, then tweak.
Good point. Thanks, Sarah.
My pleasure.
Sarah, interpreting these neural network weights, that heat map, it's a bit mind-bending.
Yeah, like looking at a secret code.
How do we figure out which features are most important?
Look for big weights. Big positive or negative values show which features have a stronger effect.
So, smaller weights mean less influence?
Exactly. Features with very small weights across all hidden units are less important.
That's helpful. What about hidden to output weights?
Harder to interpret. But, the heat map idea can be generalized.
You're saying we can look for patterns?
Precisely. Think of it like clues in a detective story.
Okay, scikit-learn's MLPs. Are they always the best?
Great for quick starts. But specialized libraries like Keras offer much more flexibility.
Keras, TensorFlow, Lasagna? What's the difference?
Keras is a high-level API. TensorFlow is powerful but low-level.
Powerful enough for GPUs.
Massive speedups. Often 10x or 100x faster.
But scikit-learn's MLPs are easy to use. Why bother?
For smaller problems or when you're just starting. But serious projects, especially on big data, use the deep learning libraries.
So, neural networks are fast, but can be complex to tune?
Computational cost is higher with complexity. You need to carefully pre-process data.
Like scaling?
Yes. Similar to SVMs. All features need similar scales or some can dominate.
How do we estimate complexity?
Count the weights. More layers and nodes mean more weights, greater complexity.
A large network with weights could overfit.
Yes, that's why we might start big. Overfit. Then shrink or increase regularization.
Right, alpha, the regularization parameter?
Controls complexity. Too little overfitting, too much underfitting.
What are different learning algorithms?
Atom and LBFGS are great for starters. SGD is more powerful but needs careful tuning.
If fit is called again on a dataset, it forgets the previous one?
Yes. A new fit is always like a fresh start.
You mentioned decision_function and predict_proba. What's that about?
Assess uncertainty in predictions. Important in sensitive applications.
Like medical diagnoses?
Exactly. We need confidence in the predictions.
So we start big, tune, then optimize for generalization?
Precisely. It's about balance.
Sarah, those plots showing decision boundaries and probabilities, fascinating.
Yeah, visualizing probabilities adds another layer of understanding.
So, what's the deal with those predicted probabilities?
They're estimates of how likely each class is.
So, if it's 90% certain, it's pretty reliable, right?
Well, not necessarily. Calibration matters.
Calibration? What's that?
A calibrated model's reported confidence matches reality.
So, a 90% probability means it's right 90% of the time.
Precisely. But an overfit model might be 99% certain. But wrong.
Makes sense. How can we tell if a model is calibrated?
There are ways to evaluate calibration. Tools and plots show how well confidence aligns with accuracy.
Okay, so, multi-class classification. How does uncertainty work there?
Similar logic. Decision_function gives scores for each class.
So, the highest score is the most likely prediction?
Yep. Predict_proba gives probabilities for each class. It's easier to interpret.
Right, so those model comparisons useful?
Absolutely. A baseline model is the nearest neighbor algorithm.
For small datasets? Easy to understand.
Linear naive Bayes. Great for large datasets.
So, what about trees and forests?
Fast don't need scaling. Trees are easier to interpret.
Random forests and gradient-boosted trees, which is better?
Gradient-boosted trees often slightly more accurate but slower.
Good to know, Sarah. How about tuning the models?
Careful parameter choices matter a lot.
What about when using different libraries?
The best library often depends on the task size and needed resources.
What about libraries like XGBoost, which use gradient boosting?
A popular alternative, often performs well, but scikit-learns are convenient for starters.
That's helpful. So, what are these plots showing us?
They show the decision boundary and how certain the model is about its predictions.
That's very helpful to see graphically.
It's crucial for understanding.
Sarah, you've covered so much about choosing models, from linear to complex neural networks. What's the best approach for a new dataset?
Start simple. Linear models, naive Bayes, or nearest neighbors are great starting points. Gives you insight about the data.
So, don't immediately jump to fancy algorithms?
Exactly. See what those simpler models reveal. Sometimes they're perfectly adequate.
You mean I can make good predictions with a simple model?
Absolutely. Plus, they're faster to train, easier to understand.
But when should we consider the more complex ones, like random forests or gradient boosting?
When the simpler ones aren't sufficient. When the patterns are more intricate or the data is larger.
So, it's about the data's complexity.
Yes, and the task. If accuracy is paramount and the dataset is substantial, consider gradient boosting or random forests.
Do you have an analogy for choosing the right model?
Imagine you have a simple jigsaw puzzle. Nearest neighbors are like carefully matching pieces. Random forests are like assembling multiple puzzle pieces simultaneously. More complexity means more resources but potentially greater accuracy.
But Sarah, isn't there a danger of overfitting with more complex models?
Definitely. But careful parameter tuning and good data representation mitigate that risk. We'll cover that more in Chapter 6.
Great. Now, how do we know which model works best?
Experiment. Try different models, check their accuracy and other metrics like precision recall.
Sounds like a lot of trial and error.
Yep, that's part of it. And remember to think about how long each model takes to train.
So, scikit-learn's datasets, important for hands-on learning?
Absolutely. Practice makes perfect. Real-world applications are more about understanding the data. Models are tools, not solutions.
Sarah, this has been insightful. Any last thoughts for our listeners?
Start with the simplest models. Learn the nuances of the data. Choose tools that fit the task.
Sarah, thank you for sharing your expertise. Listeners, subscribe to our podcast for more insights like this.
Thanks for having me, Jane. It's been a pleasure.
Thank you, Sarah. Have a great day.
You too, Jane. Goodbye, everyone.